Okay, and the last of these short videos is the divergence theorem one. So this says this: use the divergence theorem to compute a given integral. Let's see what it is. The integral over S of f dot n. So this is a surface integral where, let's see what we got here, where S is the surface of the solid region in R3, bounded by x squared plus y squared equals 1, z equals 0, and z equals 2. And we're going to set this last part a different way, defined by x squared plus y squared less than or equal to 1. This is the interior, a solid interior of a cylinder that opens. It's all open-ended on both ends. And 0 less than or equal to z less than or equal to 2. This is kind of flat plate area between volume, between these two planes, z equals 0 and z equal 2. So this is a cylinder. The cylinder centered at the a cylinder where the x and y are centered at the origin, and then extending between 0 and 2, it's got radius 1. So there are two ways of giving this surface. S is the surface of that, and this is what we need to compute. So if we're going to use Green's theorem, the divergence theorem here, then the divergence theorem says that this is the integral of the divergence of f over this region that I just described, where S is the surface of this region. Now you're integrating the divergence over that region. And so this is the integral that you want to compute. And let's give ourselves a vector field here. X, Y, Z equals x cubed, y cubed, z cubed. All right. So we've got to compute the divergence of f. So this is the trace of the derivative, or the derivative of this guy with respect to x, plus the derivative of this guy with respect to y, plus the derivative of the third one with respect to z. So the divergence is pretty straightforward. So this problem consists of knowing the divergence theorem and then being able to parameterize this tin can here. So we'll call the region D3. I'll define it as implicit region. And it's got several constraints: x squared plus y squared less than or equal to 1. Z is less than 2. And z is bigger than 0. Sort of constrained myself here. And then x, y, z. So there is the implicit region D3. It's the collection of all x's and y's that satisfy all x, y's, and z's that satisfy these conditions. So this basically gives a parameterization of that region, and now we're ready to compute. So we want to compute the divergence, 3x squared plus 3y squared plus 3z squared over this region. This is a simple integral of a given or derived real valued function. So I would implement this with Mathematica. You could write it as a triple integral, but I would implement with Mathematica as integrate or n-integrate this function 3x squared plus 3y squared plus 3z squared, where xyz is an element of D3. So simple enough, integrate this function over this region, amen. A little less than 35, I think. So those are the 3 short videos, a little bit of divergence, a little bit of Stokes, a little bit of Green. See you tomorrow.